Alright, so what we're going to be talking about today is how to find the equations that represent these functions using our graphing calculators and using regression lines. And we're going to be talking about how to find exponential, logarithmic, and it could be linear also. So just as a reminder, an exponential function that's increasing starts in quadrant 2 and goes up to quadrant 1. An exponential function that's decreasing starts in quadrant 2 and goes down to quadrant 1. Logarithmics are in quadrant 1 and quadrant 4, and logarithmics decreasing are in quadrant 1 and quadrant 4. When we talk about a concave up problem, that's what a concave up would look like. So exponential increasing is concave up, and exponential decreasing is concave up. And concave down would look like sort of like your logarithmic curves, right? Or your square root curves. So here's our logarithmic curves, and that would be concave down. Okay? So what we're going to be using is our calculators to find these solutions. So in our calculators, there's some buttons that we're going to be using. Okay, so there's a stat button on your calculator. So if you press the stat button, you'll notice that you have options to edit, calculate, test. So we're going to choose edit, and you'll notice that you get choices of lists. Okay, so here are lists that we have. We have list 1, list 2, and there's some other lists in there also. I can also graph these, and that's what these directions are basically getting you to do, is how to graph a scatter plot, which we don't really need to do, so we're not going to worry about it. But we could go to our stat plot and we could turn it on. And we would choose Scatterplot, which Scatterplot is this first option here. And then we would choose list 1 and list 2. So if I graphed this now, it would graph, let me make sure I don't have anything in here. Okay, so if I graphed now, it's going to graph what's in my information right now. So let me go back out. And that's what my scatter plot would look like. So it's not a great scatter plot, but if I change my window to, like, for example, Y-min I could put 0 and Y-max I could put 2, then I think we're going to see a better scatter plot. We can see it a little bit more better up there. I forget what numbers I put in, so let's put in 5, and this goes from 0 to 12. Let's just do that. So again, there's our scatter plot for the graph. So what we're going to do is this first example that we see here, which is talking about Olympic heights for gold medalist, and it's from 1968 to 2008. Now remember, the Olympics are every 4 years, so you've got 68, 72, 76. So 1968 will be the first Olympic, 1972 will be the second, 76 will be the third, 80 will be the fourth, and we go on through there. Now one of the things you might have to do is turn diagnostics on. So on your calculator, there's a button here that says catalog. So if you go to the catalog button and you scroll down to diagnostics on, okay, so you'll see a choice where you have diagnostic on and diagnostic off. We want to choose diagnostic on and then press enter, and all it just says is done. But now our diagnostics are on. This is going to allow us to get our correlation coefficient, which we are going to talk about. Okay, so now I'm going to go back to stat. I'm going to go to edit, and I'm going to put in the data that you see in this chart. So my first list is going to go from 1 to 11. Okay, and my second list is going to be the y values in this list, which are going to be the 1.82, 1.92, 1.93, 1.97. You see how I wrote all those in there. So I have my two lists in my calculator. So now if I go back to stat and I go to calculate, So you'll notice some different options here. We have an LINREG. That's a linear regression line. So if I think that the equation is a line, then I can choose that. The next one is a quadratic regression line. So if I think the problem's a quadratic, I could do that. Cubic regression, quartic regression, another linear regression. Notice that the only difference is the format of the equations is a plus bx versus ax plus b versus a plus bx. And then I have logarithmic, natural log regression, and I have exponential regression, and I have a power regression, which would be like something to the first power or second power, not exactly exponential. So what we're going to do, it tells us on this problem, determine the linear model and the logarithmic model for this data, and then figure out what we're going to get there. So we're going to go back to our calculators and we're going to choose the linear model. It doesn't matter which linear one I choose. And then when I press enter, notice I get these values. It's telling me basically slope and y-intercept. B is my slope, and the slope is 0.019. The y-intercept is 1.87. R squared is what we call the correlation coefficient. So the closer that R squared is to 1 or -1, the better our regression line is. So 0.75 is not too bad. So I actually wrote 0.86. So our linear regression correlation coefficient is 0.75. Okay. So now we're going to go back to stats and we're going to go back to calculate, and this time we're going to choose they wanted us to do logarithmic. We're going to choose, the logarithmic regression line, which is ln. And you'll notice this time, here's the format of our equation, a plus b ln x. A is this number, b is this number, and our r squared value is 0.92. I think I wrote 0.96. Oh, I wrote it right. So it's 0.92. So when we are looking at these two, the one that is closest to 1 is the logarithmic regression. So that's the equation that I want to use. So part B says which one seems to have the better fit, and it's going to be logarithmic. So now to write my equation, when you look at your calculator, you have the a plus b ln x. A is this number right here. So when I write my equation, okay, I'm going to write the 1.8383888882 plus b, which is this 0.0947 144975 ln x. Okay, so this value, what you see here is the model for the equation. So when they talk about select a model, that's what we've done. And now what they want us to use this model, to represent the height in year 2016, which would be x equals 13. So basically I'm going to substitute 13 in for ln x. Okay. And then when I do that, I'm going to come up with 2.08 meters. So that's saying that in the year 2013, in the year 2016, they're estimating that the high jump for the gold medalist and the high jump for women's will be 2.08 meters. And that's based on this progression of the high jumps for the years that have preceded this. Okay? All right, so then we have another example here, and this is talking about the indoor cinema sites from 1996 to 2007. So this is talking about movie theaters. How many movie theaters are there? So in the year 1996 there were 7,000. In the year 2000 there were 6,500. And then in the year 2005 there were 5,700. And you'll notice that there's a decline in the number of movie theaters. So here I said find the exponential regression and the logarithmic regression. Well, my exponential regression, when I put that in the calculator, came out to be 0.85. So again, what I'm going to do is go into Stats, and we're going to start this one, and we're going to go to Edit. And what I'm going to do is I'm going to change these first values. Again, they're going to be 1 through 12, so I need to add one more. And then my second values, my L2s, are going to be the 7,215. It's going to be the 6903, 6894, 7031, 6550, 5813, 5712, 5700, 5629, 5713, 5543, and then 5545. Okay, so now I've got all my data in my two lists, and I'm going to go look at my correlations. I'm going to look at my values. So I go to Calc, and I told you to look at the exponential and the logarithmic. So we're going to look at the exponential first. So when we look at exponential, we'll notice our correlation coefficient is 0.85. It would be in the form of a times b raised to the x, where a is the 7,438 and b is the 0.97. So exponential is 0.85. Okay. Logarithmic. Again, I'm going over to Calc and go to Logarithmic. And for the logarithmic, I come up with 0.87. Whoops, I have the wrong number written here. So 0.87. So according to this, our best line of fit should be the logarithmic. Okay, so with exponential, this was my equation that I got for exponential, and when I substituted x equals 19, because they wanted to know what was the projection for 2014, I got 4,390. With my logarithmic equation is going to be in the format 7681.545144 plus negative 0.882 0909853 ln x. And so if I substitute 19 into that problem, I get 5,161. So which one's a better projection for the year 2014? At the rate of decline here, you notice that the decline did slow down a little bit right in here. So 5,161 does make more sense. So that is more realistic. If you actually think about the year 2014, how much has it declined? And it probably hasn't declined that much more, but maybe there's less usage for those indoor cinemas. So this is how you use your calculator to come up with these regression lines, and you can do that with linear, exponential, or any others that you want to do. So on this same problem, if we looked at one more thing, if I go in and I'm not sure, I can always go to Stats and I can look at what's the linear model. And you'll notice it's 0.84. So that's still lower than the 0.87 that I had. If I go to cubic model and I look at cubic model, you'll notice that it is like negative 187. That's it's negative 0.92, which is almost implying that it's a cubic problem, but it's not. Whoops, didn't mean to do that, sorry. Which is implying that it's cubic, but if I look at the graph, I'm going to see that it's not a cubic problem. So, hope this helps. Usually when I give you problems like this, I will narrow it down and say compare exponential and logarithmic, or exponential and linear, or something like that, so you do have some sort of basis for what you're going to decide. Hope this helps.